I think it's time to go ahead and get started. Thank you to everyone who's joined us for this workshop on convenient and efficient development of machine learning interatomic potentials. It's my pleasure to introduce Yunxing Zuo, who is a senior PhD student in Professor Xu Ping Ong's group at the University of California, San Diego. He has been working in scientific computing and materials informatics areas for more than 5 years and is using machine learning techniques to address problems in material science. He is also an active coder, developing useful open source toolkits for the materials informatics community. And with that, I will go ahead and pass it over to Yunxing.
All right, thank you very much, Jared. I appreciate the opportunity to give a presentation here and share our recently developed tool to everyone. And my name is Yunxing, and I'm currently the PhD student of Professor Xu Ping Ong. Before jumping into the hands-on section, I would like to give a very brief overview of today's topic, the machine learning interatomic potentials, and this is the outline. In the material science community, sometimes people want to study the properties of the materials theoretically, whether it is for providing insights for the experimental observation or providing guidances for the experimental trials. There are typically two major computational techniques used widely today: the first principle calculation and the molecular dynamics simulations. The first principle calculation study the behaviors or the wave functions of the electrons of the materials by solving the proximity Schrodinger equations. There are many software for this, and one of the most famous is the VASP. While the molecular dynamics simulation instead study the motion of the items in the systems, and thus the Newtonian mechanics applied in here. To run MD simulations, the interatomic potentials or the force fields need to be provided to calculate the forces of the items. One of the most major software for this is LAMS, which we will intensively interact in our tutorial. In computational material science, there are three intrinsically linked aspects that evaluate the quality of a method: the efficiency, transferability, and accuracies. First principle method can achieve high transferability and high accuracies. However, the computational efficiency of the first principle is very low because of the complexity. Generally, the complexity of the first principle calculation can be at least O of n to the power of 3, which limits its scope to less than 1,000 items and hundreds of picoseconds. In contrast, the classical potentials used in MD simulations, such as the Lerner-Jones or embedded item methods, can achieve high efficiency since they are linear scaling. However, the accuracies of the classical potentials are relatively poor. The machine learning interatomic potentials provide a balance between the first principle method and the classical potentials. It provides sufficiently high efficiency by maintaining the linear scaling, but also achieve close to the quantum accuracy by leveraging the DFT calculated data as the training data. Here's the essence of the machine learning interatomic potentials, which is the machine learning of the potential energy surface as a function of the atomic positions. For each item in the collections, we obtain the local environment fingerprint by setting a cutoff radius. Within this cutoff, each neighbor items within this cutoff radius have effective interactions with the center items, and each effective interactions will be included into the fingerprints. And then we train the machine learning model y equal to fx by taking the fingerprint as the features and the DFT calculated energy and forces as the targets. And then we can the f can be any formula instance that fits. For example, the neural network, the linear regression, or polynomial regressions. We then can predict the atomic energy by using these machine learning models to arbitrary items on these potential energy surface. And by taking the derivative of the atomic energy, you can get the atomic forces of each item. Remember that the forces drives the motion of the items in the MD simulations. And there are many choices of the local environment fingerprints and machine learning models. Here we introduce four major machine learning interatomic potentials. The neural network potentials, the moment tensor potentials, Gaussian approximation potentials, and spectral neighbor analysis potentials. In our hands-on section, we will mainly focus on the SNAP potentials. But the rest potentials are also supported by our open source tool. Each potential has distinct local environment fingerprints. For example, the item center symmetry functions for the NMP and the moment tensor for the MTP encode the distances between the neighbor items and the center items, as well as the angle formed by the triplets within the cutoff. While the smooth overlap of atomic positions, the SOAP descriptor for the gap potential, and bispectrum components for the snap potentials encode the neighbor density functions. And here we show the general potential development process in practice. We generate the DFT calculated training data by using the DFT method to compute the energy and the forces of different categories of the structures. For each size of the training structure, we generate the local environment descriptors and train the machine learning model by taking these descriptors as features and the DFT calculated energy and forces as the targets. And then we optimize the potentials by tuning the hyperparameters and repeat the fitting process. And although this sounds easy, it was still tedious to prepare all the necessary files and run the programs of each potentials. And that's also the motivation of our tool. We want to make the fitting process as streamlined and automatic as possible. And now this is a part of our open source machine learning toolkits for material science. That is the MAML package. There are quite a few applications that use these codes, and all of these developed potentials have shown great performances in their study systems. For example, the phonon spectrum, the formation energy diagram, and Rayner's plots, and green boundary segregations. And next, we will use some example notebooks to introduce the fitting process of the snap potentials using prepared data step by step. For those audience who has interest in practicing the notebook, you can log in your account on the NanoHUB and go to the link nanohub.org/resources-memo and click on the launch tool to enter the notebook. Something like this page should show up. Okay, so Jared, if there's no other questions, I can start the notebook.
Sure, it looks like we don't have any questions quite yet, so that's fine.
Okay. So here is some backgrounds of the development of the snap potentials. The thought that functions and the descriptors or features are both perfect objects for automation has driven us to develop this useful and convenient tool to parameterize machine learning interatomic potentials. In this notebook, we will heavily use the MAML package developed by the Materials Virtual Lab. For those of you who are interested, please go to the official site of the package. It provides a lot of useful toolkits for material science machine learning applications. Okay, in this tutorial, we will use 3 notebooks on different purposes. The first notebook serves as an introduction of the dataset loading and local environment feature analyzing and machine learning model training. The second notebook serves as a practice of the potential development and materials properties predictions. While in the third notebook, we load some paper-implemented potentials and reproduce the results of the shown in the paper. Essentially, there's no problem if the audience have no experience with the programming or notebook, but a little bit basic knowledge of the Python is beneficial for you to understand how things work. Also, please feel free to modify the code as you need. Okay, let's work on the first notebook. We should first import the necessary modules before we do anything else. For example, the NumPy, the scikit-learn, the PyMagen, and the most important, the MAML packages. For the NanoHUB users, you should enable the lamps executable by importing the hublife.use, and we can find a serial version of the lamps. This is important as most of our code will interact with it. For the general import, we enable the matplotlib for visualization and the NumPy for the array manipulations. For the fingerprints or features, we import the bispectrum coefficients from the MAML package, as well as the principal component analysis module from the scikit-learn to analyze the feature space. And for the potential development part, we imported the snap potential objects from the MAML package, as well as the linear regression module from the scikit-learn And lastly, for the materials properties predictions, we imported the basic objects from the PyMagen package, which is a very famous and useful open source package for materials data manipulation and analysis. And we imported the materials properties calculators from the implemented in the MAML package. Okay, let's run this. Okay, let's load the molybdenum DFT calculated data. There are 6 categories of them. Each item in the data contains structural objects and the corresponding energy and the forces components. And you can see, and here shows the numbers of the structures in each categories. As you can see, there are barely 284 structures. It seems surprising that we can use less than 300 data to train a really good performed snap potentials. But in fact, it is not surprising as long as we choose the training data set wisely. We will talk this later. And as a and as a comparison, we loaded the data DFT computed data for the nickel and molybdenum systems. As you can see, the number of structures in these training data is much larger than the training data for the elemental systems. We won't use this nickel and the molybdenum data in this tutorial, but it is required if you want to train nickel and molybdenum potential yourself. So, for the local environment features, but at first, let's run these 2 cells at first, as it may take a while to run. For the bispectrum coefficients, for the bispectrum coefficients features, there are generally 6 hyperparameters we can tune. The first one is the cutoff radius. This determines the maximum range of the effective interatomic interactions. A larger cutoff will include more neighbor items, and more interatomic interactions are needed to be computed. While a smaller cutoff radius may not yield enough effective interactions with the center items. The second term is the 2J max. Sorry, it is in fact 2 times the number that limits the indices in the definition of the bispectrum coefficient. Essentially, it determines the dimensions of the bispectrum coefficients features. This value is typically 6 or 8. The third term is the element profile. The factor it sets the factor R here to scale the cutoff and the weight W for each element. Let's set the R equal to 0.5 and W equal to 1.0 as default for now. And the fourth term is the quadratic term. The quadratic term controls that whether we want to use the quadratic extension of the linear snap. This will the quadratic extension will increase the features dimensions dramatically, but the computational cost but the increase of computational cost is marginal. We currently disable this term as we may only focus on the linear snap for now. But for those of you who have interest in training the quadratic snap, feel free to go to the official site of the MAML package. It provides a lot more examples of it. Okay, and the fifth term here is the Portfit. It actually controls the output form of the features. If we set the Portfit to true, it will output 1 features per structure plus 1 features per atomic forces components, which means that we have 1 plus 3 n features for the n item structures. If set false, it will output the features per item, which means we have n features for the n item structures. And finally, the last term is includes a stress, whether we want to include the stress components for training. Currently, we disable this term as we will only use the energy and the forces as targets. So here we set the Portfit as false so that we can see 1 vectors per items. If you remember, we choose the small set of the molybdenum data from the AIMD MPT. If you remember that we have 49 structures in these categories, you can see that we have 0 to 48 structures. And each structure has 54 features, which means that the total number of features we generate here is 54 times 49, which is 2,600 features. And let's set the Portfit to false, and let's set the Portfit to truth. It will output 1 plus 54 times 3 features for each structures, which means that we have nearly 8,000 features here. As you can see, the dimension for the Portfit equal to false is 30, while the dimension for the Portfit equal to true is 31. There's an extra intercept dimensions at first of each items here. And this intercept term diminished for the forces as we disappear in the derivative of the energy. So let's see the feature distribution of each categories. Let's run these 2 cells at first, as it may take a while. A reasonable set of structures for potential fitting tends to provide a wide coverage of the feature space. However, it is impossible for us to visualize the 30-dimensional features, right? We need to reduce the features while maintaining most of the information. The principal component analysis is one of the most important dimension reduction algorithms. It creates the orthogonal basis where all the features are projected on this basis. A 2-component PCA keeps the first 2 bases, which are the two most important bases, or the principal components, which maximize the variances between the features. Remember that we have 6 categories of the structures. For each category, we extract the structure here and we obtain the features. And then we concatenate them together to fit a 2-component principal component analysis. And then, as long as we finish it, we will get 2-dimensional features instead of 30-dimensional features in here. So let's draw the let's draw the data distribution for each category. Since it may take a while, we will use the pre-cooked notebook here. This is the PSA feature distribution show. So as we can see that the AIMD structures covered a wide spread of the feature space. And the elastic surface and the green boundary data contribute additional features at the edge of the space. This implies that the AIMD structures already include a wide variety of local environment, from the high temperature melted structures to low temperature solid structures. Let's see. Okay, we have the same result here. So let's run the next 3 cells at first, as it may take a while. So above, we only get the features of a small set of structures. Here we will include all the 284 structures and extract the energy and the forces from the data. There are generally 3 lists needed. One list of the structural objects, and one list of the energies, and also one list of the forces, which is n/3 forces arrayed for each n item structures. And n can be different for the structures with different numbers of items. And here we see the structures in each items. Here the total number of the structures in the training data is 284, and then the terms in the list of the energy is the total energy for each structures, and the term in the forces list is the n/3 array, which looks like this. It's a 54 times 3 array. And then let's use the Portfit equal to true to generate the features. As it may take a while, we will still use the pre-cooked notebook here. As you can see, there are totally 47,000 features from all the 284 structures. And we have for each features, we have the corresponding target. You can see that here the target has the exact same number as the number of the features, and these targets are labeled as either the energy or the forces. And let's generate the targets per item, which means that the energy should be divided by the number of items in the structures. We fit a simple linear regression model for the features and the targets. In addition, we also want to increase the weight of the energy, since the number of the forces here are overwhelming. We increase the weight for the energy to 10,000 and keep the weight of the forces as 1. And we apply this external weight to refit the linear regression model. This is the weighted linear regression model. And as we can see, the number of parameters for the simple linear regression model and the weighted linear regression model should be the same. Both are 31. And then we want to predict the energy and the forces using the fitted machine learning models and get the errors of the energy and forces. So here we use both the simple linear regression model and the weighted linear regression model to predict the energy and to predict the x, and then we split the y into the energy and the forces by their labels. And as we can see, the errors of the energy of weighted linear regression model is much smaller than that of the simple linear regression models, which means that the increased weight of energy inform the model to take care of the energy targets. And our intuition here is correct. So let's see. Okay, finally, we got the same result, 47,000 features, and the parameters and the results here. Okay. Before we work on the second notebooks, is there any questions from the audience?
Yeah, I'm actually answering some of the the questions. And one interesting question is that from Omar, and he or she asked how to decide the configurations to be included in the database.
Yeah, so generally, as we can see here, for the feature distribution, the AIMD covering the high temperature melting structures and low temperature solid structures already cover a wide spread of the feature space in here. So the other special data, for example, the elastic data and the green boundary surface data, these are for the specific end for the potential to provide a better prediction performance for other specific properties. Okay, so let's work on the second notebook. We import the necessary modules and load the data as usual. And let's run the as usual. Okay. We also loaded the molybdenum data and nickel molybdenum data here. Let's run these two cells, as it may take a while. So to develop a complete snap potential instead of separate the bispectrum coefficients and machine learning model trainings, we wrap the bispectrum coefficient describer and the linear regression model together. These are the two inputs for the snap potential object from the MAML package. To use the trained method of the snap potentials, three lists of the structures, energies, and forces arrays are needed, which we have already shown in our first notebook. And here we will include all the 284 structures from our training data. We will split the three lists of the structures, the energy, and the forces, and we preset the weight of the energy and preset the weights of the energy and forces as an external input for the linear regression models. And here we initialize the snap potential. The bispectrum coefficient describer, as well as the linear regression models. And these are used as two inputs to feed into the snap potential object. And then in the trained method, we have three lists of the structures, the energies, and the forces, as well as one external input for the machine learning models, which is an increased weight of the energy and a normal weights for the forces. Let's use this potential for predicting the energy and forces of the same dataset. The three inputs needed here for the evaluate method are still the lists of the structures, the energies, and the forces. But in theory, the correct way to evaluate this is that we use this potential for predicting the both the training data and an exclusive the test data. That way, we can see that whether the potential has the overfitting problem, because sometimes the potential might perform really good on the training dataset, but rather poorly on the test dataset. That way, the potential has that is what we call the overfitting problems. So it looks like it may still take a while. So we will still jump to our notebook. our pre-cooked notebook. So here we shows the parity, two parity plots for the energy and for the predicted energy and the forces. As we can see that this yields the same results as previously. And that's because we use the same configuration as previously. And next, in the interest of time, we will skip the fitting process for the nickel and the molybdenum binary system. But I will definitely encourage you to try it after this tutorial. And subsequently, we want to see some other performances of our developed potentials. Okay, we're done here. So subsequently, we want to see some other performances of our developed potentials. We have some materials property calculator implemented in the MAML packages, and that takes the snap potential object as input. For example, because the molybdenum is a body center cubic metal, and we create a conventional conventional molybdenum BCC structures, and we initialize the lattice constant calculator by taking the snap potential objects, and then we run the calculate method, and we can to get the lattice constant. It's quite easy. So, and more importantly, we have the elastic constant calculator, which takes four arguments. Let's run this cell first. The first term is the potential objects, the snap potential objects, and the second term is the a typical lattice type, which for example the SC for the simple cubic, BCC for the body center cubic, and FCC for the face center cubics. And the third one is an initial guess of the lattice constant of the conventional cell. Don't worry about this, as this calculator will automatically relax the cell before calculating the elasticity. And finally, there's a fourth term. The item types, which means which specify the types of item that is evaluated. For the elemental systems, there's no other choice, right? There's only one element. But for the binary systems, for example, the nickel and the molybdenum, there are two choices. It can be either the nickel or the molybdenum. But here, if you want to choose the nickel, if we want to choose the nickel as the item type, we should change the typical lattice type accordingly, because the nickel is a face cubic center metal. Okay, next we also provided the notch elastic band barrier calculator, which takes the potential objects as input. But here, but these cells may cause the errors on the NanoHUB platform, as it requires the access of the MPI executable of LAMPs. And please feel free to contact the administrator. Run this. And finally, we have vacancy formation energy calculators. And this is relatively easy to run. So without much effort, we can train pretty good potentials for now for predicting both the lattice constants and the elastic constants, because these numbers are already quite close to the DFT calculated value. As well as the vacancy formation energy. But feel free to tune the hyperparameters as you need, because because we always want to optimize our potentials, right? We optimize the potentials by fine-tuning the hyperparameters, so that we can get a potential to predict overall to have an overall good prediction performance on all the materials properties we need. The MAML package. Okay, so finally, let's load some of the previous paper implemented snap potentials and reproduce the results in the paper with no more than 10 lines of code. And as usual, we imported the necessary module in here. And let's load the molybdenum snap potentials that is published in materials in the physical review materials 2017. And there are two files needed. The parameter file specifies the configuration of the potentials, which means the configuration of the bispectrum coefficient describer, the cutoff, the 2J max, and sort of things. And the second one is the coefficient files, which specify the coefficient of the linear regression models. And with these two files, we can initialize the snap potential using a from config. There's also another method in the snap potentials, the write param, which we will write the two files from this developed snap potentials. And then let's check the lattice constant, elastic constant, and the vacancy formation energy. The NEB barrier is disabled here because it requires the access of the MPI versions of the lamps. As we can see, these lattice constant, elastic constant, and the vacancy formation energy yields the exact same values shown in the papers. Okay, let's try to load the nickel and the molybdenum snap potentials published in Physical Review B 2018. As usual, there are two files needed. And let's check the elastic constant. Please note that the differences between the calculator for the molybdenum and the nickel, the item type here are set to the corresponding items. The first one is the molybdenum and the second one is the nickel, while the lattice type are also set accordingly. Okay. In fact, besides all these demos, the MAML package also provides a lot of variability for the users to try. Here we only show the glimpse of them. And people who are interested can go to the MAML package and check other examples. And finally, I would like to thank Professor Sheping Ong for giving me so much suggestions in developing this toolkit, and also the Dr. Chi Chen and Dr. Xiangguo Li for their generous help. I would also like to give my special thanks to Professor Adam Thompson and Dr. Mitchell Wood from the Sandia National Lab for their great efforts in developing and improving these snap potentials. And thank you all. I will be more than happy to take any questions from the audience as we have more time to answer the questions. Thank you.
Thanks very much, Yunxing. This is Alex Strachan. Sorry I missed the beginning of the presentation. I was teaching, but I enjoyed what I saw. So I think, and the Q&A was very active, lots of very interesting discussions. And so I was wondering maybe Juan Carlos or she can summarize a question that maybe came up a couple of times.
Sure.
And Yunxing can address it.
Sure.
So what are the outstanding questions?
Yeah, I'm actually in the process of answering some of the questions. And Rohit, he seems to say that it doesn't make sense to fit the energy and the forces within one linear equation.
It actually makes sense because the forces are essentially the derivative of the energy. And if you read the original the SNAP paper, which is published, I think it's 2015, in their paper, it shows three equations. The energy has an equation, and the forces has the derivative of the formalism of the energy. So we may put the energy and the forces together to train, because sometimes if we only train the energy for the systems, we might miss the derivative of it because we don't have the derivative information of it. We can call it may cause some of the like the explosion problems in the derivation of the energy.
Yeah, if I can add quickly, of course the force is the derivative, is negative the derivative of energy with respect to atomic positions. What is assumed in SNAP is that the energy is linear with respect to the bispectrum coefficients, which are nonlinear with respect to positions. So the energy is not linear with position, but linear with the descriptors. And then the force is obtained as the derivative of the energy with respect to atomic positions. And so I think that's where the confusion might come from, thinking that the energy is linear with position, which would lead to a constant force. That's not the case. The energy is linear. It's a linear function of the descriptors, which are nonlinear functions of the position.
Yes, exactly. Yes, yes.
Other questions for Yunxing?
I'm sorry. But I think you have already answered the questions. But because the energy is a linear, has a linear relationship with the bispectrum coefficient, which is a nonlinear formation of the atomic force, atomic positions. But the forces here is just the derivative of the energy, right?
Right. So this is standard MD, and the energy is conserved because the force is negative the gradient of forces. Everything is consistent like any other interatomic potential.
Yeah.
So we also have another question, and it's from Ming Shun. And the question is, if it is the nickel-moly bimetal system, isn't the structure change depends on the atomic ratios?
Yes, definitely. That's why we use in the data we loaded here. In fact, the major phases of the nickel moly is the nickel 3 and moly and the nickel 4 and the moly. You can check on the materials project, for example. And these confines the basic lattice of the nickel and the molybdenum lattice, and these are also the most interesting systems we are interesting systems we are like interested. So, but you're right. For the nickel and molybdenum systems, we also need to include the pure FCC nickel and the BCC molybdenum, and that's what we needed to train a really good perform binary potentials, because we want the potentials to predict both well on the nickel and the molybdenum, as well as the nickel molybdenum.
Excellent. Other questions for Yunxing?
Yeah, we have a question from Jinning, and she asked, how do we set the cutoff radians and the weights?
So here, I'm sorry, please go ahead.
And what are the differences between the cutoff distance and the cutoff factor?
Okay, here the cutoff radius is actually a bit tricky, because here generally we will set the cutoff radius as the second nearest number, or the third nearest neighbor's distance. But it is not really deterministic. We may want to tune the factor the cutoff radius as we optimize the potentials. This is essentially hyperparameters of the potential fitting process. And then for this, what's the difference for the cutoff scales and the cutoff is that in the formalism, in the actual implementation of the LAMP SNAP module, these factor actually scale the cutoff as the R times the cutoff of the center items as well plus the cutoff as the neighbor items. If we only have one if we only train elemental systems, the cutoff for the center items and the neighbor items are the same. So the scale here 0.5, which means that we will actually use the 0.5 times cutoff R plus R, which means we have a cutoff radius of R. But if we have two different types of the item, and these two items are set, the cutoff radius for these two items are set differently. So, and if we, for example, we have the nickel as the center item, and we have like 4 Armstrong, and molybdenum we have 5 Armstrong. If we use the nickel as the item center, we will result in 0.5 times 4 plus 5, which means we have 4.5 Armstrongs. For the nickel and the molybdenum interactions. But for the nickel-nickel interactions, we will have 0.5 times the 4 plus 4, which is 4 cutoff radius. And that's the difference between the cutoff radius, the cutoff radius set here and the scale factors in here. Did he answer the questions?
I think so. We also have another question just pop up now. So the question is, I think you are included in your study green boundaries. What kind of green boundaries have you studied? Are the atoms totally bounded, or there are dangling bonds along the green boundary, impurities or voids?
So the green boundary used here are relatively low indexes green boundary. For example, the sigma 3, sigma 5 sort of thing, because that is the I would say the most important green boundary model we want to study in the like, for example, the molybdenum elemental systems. And essentially we have some tools to build the green boundary structures, but the tools we use are also implemented in the PyMagen package. You can check it out.
I think that's about all the questions we have now. So are there any other questions?
Excellent. So let me thank everyone, all the participants, and especially Yunxing for a great presentation. I invite all of you to come next week. Shi Chen is going to present about his work, and I hope to see you all in a week for another great hands-on workshop. Thanks, everyone.
Thank you.
Yep. Thank you.
Bye.
Bye.
Bye-bye.